Okay, so the next few lectures we'll um, look at some basics of transistors, MOSFETs. I believe this is chapter 2 in the textbook. So as you know, the transistors are made on a silicon substrate. Basically, silicon has a very nice crystalline structure. Um, a pure silicon, also called intrinsic silicon, doesn't have too many free carriers. Okay, so each silicon atom has four valence electrons, so it forms bonds with four other silicon atoms. So it has a nice tetrahedral type crystalline structure, and all the electrons are kind of tied up. So, but always due to some you know thermal excitation, you'll have a few electrons which are free, uh, and there's not that many of them. Now, of course, when you heat it up, you'll have more electron hole pairs formed, and so the silicon material becomes more and more conductive as you heat it up. Whereas a normal resistor, when you heat it up, the resistance goes up. In the case of a semiconductor, it actually goes down. Now, you can change the conductivity of the silicon by adding some impurity atoms. That process is called doping. So, when you add an atom from the fifth column of the periodic table, those elements have 5 electrons in their outer shell. So, so for example, you take arsenic out here. So, the arsenic goes and embeds itself in the crystal lattice, and it has an extra electron, right? Because the 4 of them are tied up in bonds, an extra electron is free, and it just kind of roams around, and it's available for conduction. So you can change the conductivity of the silicon material by adding a dopant atom, and this kind of material is called an N-type material because N stands for negative. So extra electrons you are kind of introducing into the material, it becomes conductive, and the majority carriers are electrons. Now there is, if you take an element from the third column of the periodic table, like boron for example, and you put it into a pure crystalline silicon, because it has one electron less, it's kind of like a hole. And the only way to understand these holes is through quantum mechanics. But for the purpose of this class, we'll assume holes are just positive charge carriers. Okay, and then they are the other kind of carriers which are available for conduction. Typically, you have this parameter Nd or Na, which is the concentration, that is the number of atoms per unit volume. That is an important number, and that kind of determines the number of carriers, the majority carriers which are available for conduction. The more you put, the better it is in conducting. So this is how you can take almost insulating material like silicon and change its properties of conduction by introducing this impurity atoms or the dopant atoms. So you take an N-type material and a P-type material. What is an N-type material? It's a silicon which has N-type dopant atoms like arsenic. So that means there are excess of electrons. You have a P-type material where you have doped the silicon with boron type of element 3 from the third column periodic table. So you have excess of holes. So when the two come together, there is a junction formed, and this forms a device called P-N diode. So what happens is that on one side you have an excess of electrons out here, and on one side you have an excess of holes, right? So you have this, it's like you have a tank of water and you open the tank, the water will start flowing, right? So this kind of what happens is excess of electrons. As soon as it's connected with a material where there is not too much electrons, the carriers just diffuse across. Okay, similarly holes from the p-type start diffusing across to the left. Now when the carriers from the left, that is n-type, start diffusing across, what they leave behind is the dopant atom. Remember the dopant atom, in this case arsenic, it gave the electron. So when it loses the electron, it becomes positively charged. So what you have is fixed positive charges which are embedded in the silicon lattice. Similarly from this side, when the holes start diffusing to the left, they leave behind acceptors, the dopant atoms which become negatively charged because they have acquired one extra electron to form the bond with the silicon. What that does is now you have an electric field which is set up, and this electric field acts to counteract the diffusion. At some point you reach a balance where there is no more, everything reaches an equilibrium, and you have what is called a built-in potential, and you have this notion of a depletion region, because in this region the excess carriers are not there. They're all diffused across to the opposite region. So this is a depletion region which essentially has just some minority carriers and the fixed dopant atoms. There are some equations out here which basically, just based on some basic electrostatics and Poisson's equation, you can kind of arrive at these, where you can calculate the built-in potential, you can calculate the depth of these diffusion regions and so on, depletion regions and so on. Okay, so in this equation D2, this is a simplified equation when the dopant atoms, the density of atoms here, dopant atoms, is very high on the left side, n side, so that's why it's labeled as n plus. Whenever you have n plus label, it means it's very heavily doped. And p type means it's kind of moderately doped, and n plus, the electrons diffuse across. So it turns out that at the end of the day you need to have charge balance out here, because there is very high density on the left side. The depletion region can be very thin and still support the charge required to balance on the right side, on the p side. And so the depletion width is largely governed by the width of the p side, and it's given by this equation where phi bi is the built-in potential, Na is the acceptor concentration, Q is the electron charge, epsilon s is the dielectric constant of the silicon. Now in this Pn-Junction, when you apply electric potential across it, in the forward bias you have, as you might have all studied in your basic electronics, this you cannot tell that you haven't seen before. So essentially there is exponential increase in the current up to a certain point beyond which the device will break down. Similarly on the reverse bias side, there is not much of a current flow till some point after which there is a breakdown and there is a lot of current. Now the thing is that the current equation is given in this fashion. For the forward bias, phi t is the thermal voltage, K is Boltzmann constant, T is temperature, Q is the charge. And the important thing here is that this I naught, which is the current when it's reverse biased, is a strong function of temperature. Okay, that's again comes back to silicon and how when you have higher temperature you have more, you cannot break the bonds and you have more free carriers available for it to conduct. Now in digital CMOS circuits, we don't like diodes. Okay, diodes are bad. Diodes are parasitics. We don't like diodes, but we can't help it. We have to live with it, as we'll see. If you recall from the previous lecture, for the MOSFET, there is a n plus. There is a source drain region, which is either n plus or p plus, depending on the transistor, and that along with the substrate forms a diode. We would like to keep all diodes to be reverse biased. We don't want to forward bias any of the diodes in CMOS digital circuit design. Okay. So that is basically the way we use diodes. We cannot tolerate diodes in digital CMOS design, and they do two things to our circuits. One is there is leakage. You see, when the diode is reverse biased, we like to keep it reverse biased, because if we keep it forward biased, there is a lot of current which goes through the diode, right, in the forward bias, and it will take away from the computing you want to do. You kind of want to move around and play around with the currents and charges to do your operation, but this essentially sucks out. And in the reverse bias, ideally there should be no current, but you end up with this current leakage. Essentially, it's a leakage current. So you have a diode which is reverse bias, but it's going to take up a small amount of current, and if you have too many diodes, it becomes a problem, right? The other way in which the diodes affect our circuit is by introducing capacitance. If you look at this out here, you can think of this as a parallel plate. There is positive, a capacitor consists of two plates, positive charge and negative charge, with a dielectric separating them. So when I'm reverse bias, it's pretty much like a capacitor. I have positive plate and negative plate. So, and whenever you have capacitance, that is basically a parasitic. It slows down your circuit. Okay, so that is basically the implication of having a diode in a digital CMOS circuit. And once I know the distance of the parallel plate, and based on based on the charge density and the which is Na acceptors, is the number of acceptor. For every acceptor there is a charge, and so the acceptor concentration is the charge density, and D2 gives me the area, so that gives me the total amount of charge, and then the distance between the parallel plates, which is kind of given by D2, together gives me the capacitance. Epsilon A by D. A is the area of the plate, epsilon is the dielectric constant, D is the separation of the plate. So that's the basic formula for the capacitance. Here, of course, we are looking at capacitance per unit area. In this equation, this is what is called a small signal capacitance. So this is a concept which is typically used in analog circuit design. This capacitance is a nonlinear capacitance. Why? Because the plate distance changes. As I apply more and more reverse bias, what happens is that more and more depletion happens. So my depletion widths extend. So you see my plate distances are changing with the voltage. So capacitance is a function of voltage. So it's a nonlinear element. So what this equation is telling me is at some particular point, if I give a very small AC signal, what is the capacitance seen by that signal? That is the small signal capacitance. Now, clearly in digital CMOS circuits, in analog circuits, small signal analysis is very commonly used. In digital circuits, we don't use small signal analysis. Okay, so but still this equation is kind of useful just to keep in mind how it affects. In digital circuits, you have large signals. Signal swings always go from 0 to VDD. So you have to essentially consider completely the nonlinear effects of the capacitor if you really want to correctly analyze the behavior of the circuit. That is typically very difficult to do by hand because these equations are very complex. So you have numerical techniques, numerical integration, which is done in SPICE to actually solve and give you more accurate results of the impact of these capacitors. One very important concept in MOS technology is this concept of inversion. So now from what we have here is essentially what is called a MOS structure. You have semiconductor, you have oxide insulation, and on top of it is the gate. Okay, it used to be metal gate before, now then it became polysilicon material for the gate. Now again people are going back to metal. Why use different materials and so on? That is again something which is part of what is called device engineering. You have to engineer their transistors. You have to play around with a lot of material properties, their electrical manifestations, and kind of design your transistors. Again, this is something which if you were to take a device physics class, you basically study those. Here for us, you have a gate which is with an insulator and a body. So this looks like a capacitor, and it is indeed a capacitor. The thing with this structure is that depending on the, so what you have is here is a P-type body which is fully depleted. Okay. Well, its state depends on the actual potential. So here what you have is the P-type body where it becomes basically when you apply a negative potential between the gate and the body, you have negative charges in the gate, so that attracts positive charges. So a P-type anyway has a lot of holes, and you are kind of also encouraging holes to be around, so it becomes more P-type. So it essentially what we call it goes into the accumulation region. Vg less than 0, you attract holes, and this is the situation you have. Now, we don't use again this regime of operation in digital circuits. We don't use accumulation mode in digital circuits. Now, when we apply a positive voltage, Vg greater than 0, you have positive charges on the gate, which you can say repels any negative charge. What are the negative charges? These are the minority carriers, the electrons. So they get repelled. And when that happens, you get a region here which is depleted of free carriers. Right? So you had put dopant atoms which created some free carriers, but now they are being depleted. The holes are being repelled, so it's getting depleted. And you're just left with some minority carriers, which are not too many. But as you make it more and more and more positive, something really interesting happens, and this thin layer at the surface, at the interface between the silicon and the oxide, you start seeing a lot of electrons. In fact, you can get to a point where there are as many electrons as you would have had if you had actually put an n-type dopant atom. So you have inverted the nature of the material. What was a p-type material? Electrically, you have inverted it to look like an n-type material. So that is what is called inversion. Okay. So the three modes are accumulation, depletion, and inversion. Now in digital circuit design, we typically operate either in depletion region when transistor is off, or in inversion region when the transistor is on. So those are the two modes or regimes of operation of transistors in the digital circuit. Note that this is not a transistor, this is just a portion of a transistor, essentially the channel region. We have not shown the source drain region out here. If you notice out here, there is another parameter here called Vt. This is again a very important parameter, Vt, that is the threshold voltage of the transistor. We can kind of think of the threshold voltage as that voltage at which you have inversion, a strong inversion happening, where the concentration of the free carriers is the same as the acceptor ion concentration. Na was the acceptor ions to make it a p-type material. By applying a voltage, you have inverted it, and the carrier concentration has become the same as what the acceptor concentration is. So there are various definitions of Vt. This is kind of one definition where we would like to, kind of where you say, okay, now I have inverted. What was the p-type has become an n-type. Of course, in nature, nothing is dramatic. You never have either it's inverted or non-inverted. It's a gradual process. So what it means is that when, even in this region, when my gate voltage is less than the threshold voltage, I have some inversion, because there is some positive charge here in the gate. It is starting to attract some negative charges. So the channel or this region is, the surface here is slowly getting inverted. So there are various degrees of inversion. Weak inversion when it's just starting to invert, moderate inversion where a little bit more, strong inversion where you have really high concentration of electrons, as much or more than what is there in the rest of the body. The rest of the body has Na, acceptor ion concentration. Here you have at least that much or more. So this is an important point. In digital circuit, we kind of like to think in binary, 0, 1. Okay, and to a large extent, our design, everything is based on that. But when you really get down to the lower level and look at what is happening, the physical phenomena, you find that things are continuous and analog. And this has an implication from the perspective of performance, power, leakage, etc., etc. And this will become clearer as we go along. So in this graphic, what we are showing is the concentration of the electrons at the surface region out here, at the just below the interface, as a function of the gate voltage. So on the x-axis is plotted the gate voltage, and basically the concentration grows exponentially. Okay, so that is why you kind of see this like a hockey stick. The same curve you'd have seen in the diode current also. I versus V, you have a hockey stick curve. This is the curve. Of course, when you were to plot the log of the concentration of the electrons, it will look like a straight line, log of that versus Vt, but if you just plot in the linear scale, it will look like a hockey stick. So when the gate voltage reaches about Vt, the concentration is the same as Na. Na is the concentration of acceptor impurity atoms which you have introduced to make the material p-type. So this, as I said, this threshold voltage is an important parameter. Because for digital circuits, it's like if I'm below threshold voltage, okay, even though there is some concentration here, but this is an exponential scale. Very quickly, in every 100 millivolts, you have a drop of 10 in the concentration. 300 millivolts, you have 1000. 400 millivolts, you have 10,000 difference in the concentration of strong inversion and the voltage less than that. So at some level, you can kind of say that this Vt is kind of like the threshold. That is why it's called a threshold voltage, below which I can kind of say the transistor conductance is very poor, so it's off, and above it is on. So the threshold voltage is a very important parameter, and a number of factors influence the threshold voltage. So this is like one of the most important parameters when you engineer the transistor. If you are a semiconductor device person, you are actually engineering this transistor. So this parameter, really you pay a lot of attention to try to set it to where you want. Typically this is about 300 to 400 millivolts, but it depends on a number of factors. There is a baseline threshold voltage which you get based on the material properties of the gate of the bulk. This is called the bulk or the body. Okay, so that sets a baseline. But in addition, the actual potentials, the potential of the body with respect to the gate also affects the threshold voltage. So again, it's a kind of a complicated phenomena. The threshold voltage itself is not a constant. It keeps changing based on the electrical potential of the body. This is the body. Electrical potential affects the threshold voltage. It's a very weak effect. Now, typically, as I said, in digital design, we take the body and connect it to ground for the nMOS and to VDD for the PMOS. So we don't want to play around with that. But you can actually play around with that body voltages to modulate the threshold voltage, and that is used in certain places. Okay. So now, when I have this structure and I think of it as two reservoirs of electrons. There are two n plus regions on either side of this channel. There is a channel, okay, which consists of essentially this is the p-type body which has a lot of holes. There is an insulator and there is a gate. Okay. The important thing is the gate potential modulates the number of carriers you have in the channel. More carriers means you can imagine more conductivity. Less carriers means less conductivity. So in some sense, you have created a device where you can control the conductivity through a third gate. So the connection between the source and drain, what the quality of the connection is determined by the potential at the gate. So you have the source and the drain which are n plus. That means they have a lot of electrons. You have the channel which is p-type. So there are not too many electrons. So under normal circumstances, the source and the drain cannot exchange carriers because there is a barrier. Okay, so that is shown graphically on the right side out here, where you have a water tank, two water tanks are there, and then there is this barrier. Water cannot flow from the left to right. Okay, so the barrier height can be adjusted based on the potential you apply to the gate with respect to the source and the drain. So here you see this is the gate node G labeled as G. Excuse me, I'll just switch off the lights here. So you have the gate voltage, which as you start making it bigger and bigger, okay, what you're doing is you're reducing the barrier height. Because as you make the gate voltage higher and higher compared to the source, you make the gate positive, you start attracting electrons. So you start inverting the channel. So once I start inverting the channel, now I have a path between the source and the drain, and that's what happens out here. You see the gate falls below, and now I have a channel to connect the two reservoirs. That's fine, but nothing happens unless I make the height of the two reservoirs different. I won't have water flow. Similarly, unless there is a potential difference between drain and source, even though the channel is formed, there will be no current. Yes, a channel is formed, but there is no current here between source and drain because there is no potential difference. So when I apply a potential difference between source and drain, I will have flow of, because now it's a conducting channel, I will have flow of current, very similar to out here. Except what is interesting is that for a particular potential of the gate where the wall, this barrier has come down to a specific location, as I change this potential of the drain, as I make the drain more and more positive, in this case I make the reservoir lower and lower, there comes a point, see out here what happens as I make the heights of the two reservoirs different, there is a gradient. You can kind of imagine intuitively that the amount of water flow, the flow rate depends on the gradient. Steeper the gradient, faster will be the flow of water, and so more is the flow rate. But so as you increase the drain source voltage, the gradient becomes larger and larger, the current increases. For any particular gate voltage, as you increase the drain source voltage, gradient becomes larger, current increases. But up to a certain point. Beyond a certain point, there is this notion of pinch off where I cannot change the gradient anymore, and so the current flow between drain and source remains constant. Okay. So what have we looked at here? For a given gate source voltage which is positive, that means you have formed the channel for the gate source voltage, the current as a function of drain source voltage. In the beginning it goes linearly, but beyond a certain point it just saturates. I cannot increase the current anymore. There is current, but I can't increase it. So this is just a simple kind of way of understanding this characteristic of the transistor using this fluid flow model. Suppose I ask the question, for a given drain source voltage, I increase the gate source voltage. Let us take this case. I fix the height difference between the two reservoirs, but I increase the gate source voltage. That means I make this lower and lower. As I reduce the barrier lower and lower, I am going to allow more and more volume of water to go through, so the current will go up. So the current as a function of gate source voltage will increase continuously, right? Whereas the function of drain source voltage, it will go to a certain point and saturate. So, so that's basically the important aspect out here for the transistor from the point of view of currents as a function of voltages. So you have three nodes: drain, gate, and source. You also have the fourth node, which is the body, which I already said for digital. Typically, you connect it to ground for nMOS and VDD for PMOS. Okay, there are three regions of operations as we saw before. You have a cutoff region. That means when the gate voltage is less than the threshold voltage, right? It's really the threshold voltage which determines when you have a channel or not. So when I'm less than the threshold voltage, I can kind of say that it's beginning to invert, but it's not really well, there is no good connection, so the current is almost zero. Okay, so this is the first order model. Okay, let's think of this as a first order model. When I have a channel form, but the drain source voltage, now I perturb it a little bit. So there is flow of water, there is flow of electrons, and as I increase the drain source voltage, the gradient becomes more and more, so the current increases. So that is a linear region. Current is a linear function of the drain source voltage. It's kind of pretty much like a resistor. You have a voltage controlled resistor. The gate voltage determines the resistance value. Okay, so essentially you have a voltage controlled resistor, which is very useful for if you're doing analog circuits and you want a voltage controlled resistor, you can use that. And then you have a saturation region where the drain source voltage is so large that the channel is pinched off at one end, at the drain end, and any change in the drain source voltage doesn't really affect the gradient, and so you have a fixed current. So this is called a saturation region. So depletion when there is no current, strong inversion when you have a channel form, and in the strong inversion, depending on the drain source voltage, either you have linear operation or saturation, right? So these are the basic regimes of operation. So in a circuit, when if you take a circuit, the voltages are all switching around. The transistor will cycle through all these different regions. When the voltage of the transistor at the gate is 0, transistor is in depletion. As you start applying the positive voltage, it starts inverting, and if there is a non-zero drain source voltage, the transistor enters a saturation region, gets into linear region, and so on. Okay, that is what happens in a digital CMOS circuit, because the voltages are changing by very large amounts. The transistor kind of keeps cycling around in between all these different states. Whereas in analog design, you keep the transistor in a particular region. If I want a resistor, I'll keep it in the linear region. I'll bias it, I'll set it in the linear region, and the voltage swings are all small enough that I remain in that region. If I want a current source, I'll keep it in the saturation region such that the currents remain constant. Whereas in digital circuit, my swings are so large that my transistor keeps going around between all these different regions. So this fluid flow model is kind of nice from an intuitive point of view, just to understand what's going on. It will not completely capture all the detailed phenomena of currents as a function of voltages, but for the purposes of us to work with transistors, I think this is a kind of a good model to go with. So this is basically the curves of the current, that is the drain source current, okay, as a function of the drain source voltage. When the gate voltage is low, that means gate voltage is less than the threshold voltage, I don't have a channel formed. In that case, the current is 0 throughout. No matter how much drain source voltage I apply, I cannot get current to flow through because I don't have a channel. So the curves for VGS less than VT all fall on the x-axis. Okay, as I start increasing the VGS, I get more and more inversion in the channel. So essentially, I can get more and more current. So when I have VDS very small, remember I'm just slowly tilting the balance between the two reservoirs. So I get a linear increase in current. Beyond a certain point, which depends on the gate voltage. For different gate voltages, the point of reaching saturation is different. So for example, if I take VGS equal to 1.5 curve, at this point I enter the saturation region. My channel is pinched off. I can't change the gradient anymore. So my current starts becoming constant. So this is a function of IDS, that is drain source current, as a function of drain source voltage for different gate source voltages. Gate source voltage less than threshold voltage, the currents are 0. Okay, that's not shown out here, but basically that's what it all falls on the x-axis. Of course, I can plot the drain source current as a function of gate source voltage also. Right? How will that curve look? I just described it in a text form. I mean, not text form. I described it verbally. So basically, IDS as a function of VGS. So it will look like there is a point here VT, VDS is constant, so a digital representation will it'll kind of look like this, but really what happens is you have something like this. So in fact, this is also used as a way to measure the threshold voltage of a transistor, either in simulation or in the actual, when you fabricate the device, you want to measure the threshold voltage. What is the threshold voltage? So you put some VDS equal to some small value, VDS equal to 0.1, and then you measure ID versus VD, and then extrapolate and see, you say this is my threshold voltage. You take the linear region and then extrapolate, and you say that is my threshold voltage. There are a couple of different ways of measuring threshold voltage. They all give you slightly different numbers. But okay, so this is one way of looking at it. So in the case of PMOS transistor, basically what you have is you have holes which are required to form the channel. So sometimes PMOS and NMOS can become a little confusing. In the case of NMOS, the gate has to be larger than the threshold, the source. VGS has to be bigger than VT to get conduction. In the case of PMOS, VGS has to be less than the VT. So the gate has to be less than the source. So then when the gate is negative, it will basically pull the holes. Like in NMOS, when the gate is positive, it pulls the electrons. In the PMOS, the gate is negative with respect to source, it pulls the holes. Okay, and then that is why if you see out here, the curves are all drawn like this. There is ID. The signs are negative, positive. I mean, it's depending on which direction you are measuring the current. So you have essentially it's mirrored out here, and you have a similar behavior. One thing is that if you look at the transistor, if you had two transistors of the same dimensions, the currents will be different. We'll see that next, because the current also depends not only on the potential but also on what is called mobility. How mobile are the electrons or the holes? How mobile are the carriers? The hole mobility typically is lower, 2-3 times, but again it depends on specific technologies and so on. Sometimes you can have hole mobility to be as good or better than that of electron mobility also, but typically, at least the kinds of vanilla processes we deal with, the currents in the PMOSs are factor of 2 or 3 less than the currents in the NMOS for the same potentials you apply. So, let's kind of go a little bit more deeper into this current equations, just to get an understanding of how you would kind of go about calculating these currents. Of course, we won't be doing this too much in this course, but it's still kind of interesting because it's pretty simple and straightforward. And this is kind of how even more advanced models kind of really look at to calculate current or come up with models for currents as a function of the voltages, because those models are very important for you to actually do any simulation. You need to have those models called what are called compact models, which are required for you to simulate your circuit. So what the basic idea is very simple. For any particular potential at all the nodes, you find how much charge is there. That is the most important thing. You have to calculate the charge, because then the flow of charge, current is rate of flow of charge. Once I know the charge, I can calculate the current from there. So that is the most important thing. So, so here what we have is a perspective view of a transistor. Remember in the previous pictures, we were just looking at this face. We had just taken a slice through the transistor, where we had the source and the drain region, the channel and the oxide. The distance between the source and drain is a very important parameter. It's called the channel length, the length of traversal of the carriers. Now this depth out here is the width. So you see, this is how the transistor looks like in perspective, right? So there is, this whole thing is the gate region. You have the width, you have the length. As a circuit designer, what is it that you have in your control? When you design a circuit, what does it mean? Of course, you figure out the topology, how you hook up transistors. The other thing you have to do is, what are the sizes of the transistor? What do you mean by the sizes? For a circuit designer, it's essentially the channel length and the channel width. So you can decide what should be the length. You can decide, there is a minimum length which the technology will provide. That is basically, as we said, when someone says it's a 130 nanometer or now 14 nanometer, you have the spacing between the source and drain to be 14 nanometers. Okay, that is a minimum. You can't go lower than that, but you can go higher than that. Okay, we'll see. And then similarly, width is completely in your control. What is the implication of length and width? When I increase the length, you can kind of imagine that in the linear, in the direction of traversal of the electrons, you're putting more stuff. So the resistance will go up, currents will go down. That's kind of the first order basic guess one would make. What about the width? When I increase the width, I have many Exactly. I have many parallel, I can think of it as many parallel transistors. So I can increase the current. So lengths and widths allow you a knob to control the amount of current you can use in your circuit. Why is that important? Because power. Okay, and area. You would like to use the smallest area possible. So if the technology allows you to define the minimum channel length and width, you would want to use that, because then you can keep the area small, and area translates to cost. It turns out cost translates to profits, money, etc. etc. So area you want to keep small. We'll see as we go along, that is an implication. When you keep the area small, when you keep the width small, you don't have that much current. And in a circuit, as we said, we have capacitors all over the place. You have to charge and discharge capacitors at the end of the day. So if you have very less current, it will take longer to charge and discharge capacitors, because you still have to charge up to VDD or ground. You remember, these are digital circuits. The voltage levels are the same. Capacitors are okay. There is some dependence on the size, but there's a lot of capacitance which is independent of the size of the transistor. You have to have wires and so on. They're all fixed. As you reduce the size of the transistor, you have less current to charge discharge, so it takes more time. So you slow down. On the positive side, when I reduce the size of the transistor, I reduce the currents and I reduce the power. So smaller size is good for area and power, but not good for speed. So there is a trade-off out here. That is typically what happens when you do engineering. You have these trade-offs. It's very difficult to say, because if you try to squeeze one, the other side blows up. So you have to find an optimum across all this. Okay. So, so if you look out here, again we come back to the cross section. There is a capacitor out here, Cg, which is the gate capacitor. What is called the gate capacitor? There is a dielectric, it's an insulator, and you have a channel formed, and the channel is right at the surface. This cartoon representation seems to show there is a certain depth to the channel. Okay, but in reality the channel is pretty much at the surface. So it's like a sheet, 2D sheet, and you have the other plate of the capacitor. So you have pretty much a parallel plate capacitor Cg, which is between the gate and the channel. If Tox is the so Tox is the spacing, that is the thickness of this oxide. Epsilon ox by Tox times area. Epsilon A by D is this capacitance value. What is the area of the plate of the capacitor? This whole thing is the plate of the capacitor, right? L times W is the area. Tox is the distance. So epsilon A by D is this gate capacitance. So what is the charge out here? Charge on that capacitance is Cg and the gate to channel minus Vt. Remember that the channel forms only after the gate voltage exceeds the threshold voltage. So that is why we have to kind of pay a tax, toll tax. Vt is gone, so you have overhead, what is called overdrive, not overhead, overdrive, Vg minus Vt. Okay, Cg times Vg minus Vt, which is the charge in the capacitor. In the analog design, this gate overdrive is again an important parameter. You want to set the gate overdrive in your circuit design. In digital design, we don't worry too much about setting it, because Vg, typically when I turn it on, Vg goes all the way to VDD. Okay, so I don't really control Vg, but of course analog design you control it. So you have channel charge out here, Cg times Vg minus Vt, which is the overdrive. Now we said VGC, so we are looking at all points across the channel. The potential across the channel is different, because on this side it is the source potential, whereas on this side, on the right side, it is the drain potential. So the channel potential is different, it's not constant. So I can kind of basically use a average value, source to drain, and then Vs plus Vds by 2 becomes the average channel potential. And so the average gate to channel potential becomes Vg minus Vc, which is Vgs minus, so you just put it out here. Vg minus Vc, I substitute Vc from above, it becomes Vg minus Vs, which is Vgs minus Vds by 2. And the capacitance is Cox WL. So my channel charge QCH is essentially the capacitance times the voltage. C times V is the charge square. Okay, and V is, we are taking the average value, Vgs minus Vds by 2. Okay. So you see that it becomes out here, I'll come back to the last equation out here. The Q channel, the channel charge is the capacitance, which is Cox W by WL. Okay, the Cox WL times the overdrive. Overdrive is VGS minus VT minus VDS by 2. Okay. Now that is the channel charge. I should have probably put an equation for channel charge out here just to make it clear. Now once I have the channel charge, the charge is moving because I have put in a gradient. And there is a velocity of at least the charge mass. There is an average velocity called the drift velocity. Okay, that is V. And that velocity depends on the mobility and the electric field. Larger the electric field, faster it will go. Right? So there is a mobility factor out here, and the electric field is VDS by L. We are talking of this lateral mobility. Okay, lateral electric field, VDS. Electric field is voltage by the gradient of voltage is electric field, right? So VDS by L, L is the channel length. So now, what is the current? Current is the charge, how long it takes to traverse the distance L. Transit time, charge by time. Time is the distance traversed by velocity, L by V. You plug all of this in and you get this kind of equation. Now, this is a very, very simplified equation. I mean, but the approach is the same when you want to do modeling for even more complex, if you want to do more and more realistic modeling, except there are a lot of, the voltage will not be linear drop in voltage, it will vary in a different way and so on. You might have to account for some, mobility might be a function of voltage, all these kind of things kind of really come into the picture and you have to take that into account when you come up with the equations for modern transistors. But the approach is the same. You find the charge, you find the velocity, you find the time it takes to go across. So it's a very simplified model which gives you this. And this model actually was working well till about maybe 20 years back. So what is called the long channel model. When the transistor channel lengths were a few microns, it worked well, and you could describe very nicely the transistors using these simple equations. Okay. In the saturation region, what happens is you reach a pinch off, after which it goes into saturation. So at the point of pinch off, the voltage VDS is such that there is no channel formed at the point of pinch off. There is no channel formed at the point of pinch off. I lose the channel because I just pinched it off, which means there is no more overdrive out here at this point. Only when there is an overdrive, I have a channel. When I don't have overdrive, I don't have a channel. So VGS minus VT is what the drain source voltage is. And I need to have continuity of the equations. Whatever was the equation in the linear region, this previous equation is in the linear region. As soon as I go to saturation region, at that point of entering the saturation, I have to have continuity of the currents because the same current remains in the saturation. So you just plug in the value VGS minus VT and you end up with this equation. The drain current is mobility times Cox, which is the unit capacitance, W by L, because you put in the equations for area and all that, it comes out like this, times VGS minus VT whole square. So it's a quadratic. Okay, so this is the equation in the saturation region. Okay, so VGS less than VT, linear region, VDS less than VD sat. Sat is the point at which VD sat is the voltage at which transistor enters saturation, and then you have saturation region when VD is bigger than VT, where current is independent of the drain source voltage. It's flat. If you remember that curve, current as a function of drain source voltage is flat. Okay, so this is basically the long channel transistor models. Of course, in reality, this kind of model doesn't work anymore. So this is what the black curves are, the curves given by the model based on fitting to certain key parameters. But actual currents are, you see two features. One is the currents are less. Second, I don't have this flat here like this, horizontal, whereas the curves are going up. Okay, and thirdly, the spacing is growing. Why? If you take a particular VDS and I look at the current as a function of gate source voltage, it's a quadratic. Every increment in gate source voltage will give me more and more increments in current because it's a quadratic thing. It's not a linear thing. Whereas here you see the increments are almost the same. So what you can infer is the gate source voltage doesn't come as a quadratic in the equation for current. It's more closer to linear. So these are all the complications of modern transistors. Okay, so this is where we are with respect to modern transistors. In addition, we have another problem, which is the transistor, which is where I have a drain source voltage, but I have my gate source voltage is less than Vt, where we said the transistor is off. It's not really off. We use, because you see there is still some channel form. If there is some positive gate source voltage, it will attract some amount of carriers. So there will be some small amount of inversion, and you will still have channel and you will have some current. Before you could ignore that current. The overall currents in the system versus this small current when it was there, you could kind of ignore. But now, as we are going forward, we will kind of study that a little bit more. Those currents we can't ignore. So that is called a sub-threshold leakage current. What is it? You see, this is a simple inverter structure. There is an nMOS, there is a PMOS. When my gate voltage is 0, my nMOS is off. Let us first understand the logical functional operation. Whereas when a gate voltage is 0, the gate to source, remember for a PMOS, the source is at the top. That is the source of holes. Source means source of majority carriers or minority carriers. Here, source is at the bottom, source of electrons. So when my A is 0, I have a negative voltage, so the PMOS is on. When PMOS is on and NMOS is on, what that means, Y is connected to VDD. There is a good, nice connection to VDD. So output is 1, logical 1, electrically VDD. Similarly, when A is 1, NMOS is on, PMOS is off, so Y is to 0. So I have a logical gate you can make as the inverter. Now when A is 0, NMOS is supposed to be off. And Y is VDD. So now I have a drain source voltage which is not 0. If you look at the simple model which we just saw for the current, long channel model, we would say there is no current. IDS for the NMOS, there should be no current here. But, there will be some small amount of current. That is the leakage current, the sub-threshold leakage current. Okay, so that is basically what is shown out here. So in this graph, which is now plotting IDS versus VGS, remember we had that quadratic equation, but in this graph we are plotting IDS in a log form. Logarithmic IDS versus VGS. And there are two features to see out here. In this region, you see log IDS is a linear function of VGS. So that means ID is exponentially dependent on the gate voltage in this region, which is less than the threshold voltage. We are focusing on this. This is the threshold voltage. We are looking at the regime out here. Okay. Secondly, there are two curves here. VDS equal to 0.1, VDS equal to 1.0. Of course, when I increase VDS, for any given VGS, current goes up, which is okay. I mean, this current goes up when I put more potential, which is reasonable. So you have two curves. Larger VDS means larger current. The other important thing is out here. When VGS is 0 and VDS in the ideal model, no matter what VDS I apply, the current should be 0. But here there is some current, 1 nanoamp, 2 nanoamps. Similarly, if I increase VDS, the current goes up somewhere. So that means you have some current. These currents are called sub-threshold leakage current because I am less than the threshold voltage. So it is sub-threshold. So that current is sub-threshold leakage current. And there are certain additional features here. We'll look at that later, maybe in the next lecture, what are called gate-induced drain leakage, drain-induced barrel loading, etc., etc. So, well, the point, at least Dibble, let's look at this. DIBL is drain-induced barrel lowering. What it is saying is that as I increase my drain voltage, even when there is no gate voltage, my current is going up. So somehow the barrier is reducing. The barrier to prevent, remember I had the wall up to prevent water flow between the two reservoirs. Now I'm putting a gradient. As I'm lowering the reservoir, I'm somehow also reducing the barrier. So the drain is having an impact on the barrier height. Okay, so that is one of the non-idealities. That is called drain-induced barrel load. Okay, so with that we come to an end for today's lecture, and Friday is a holiday. We'll continue on Monday.